June 27th, 1943. Wilhelmshaven, Germany. Oberstingenieur Klaus Richter stood in the wreckage of what had been a B-17 flying fortress, his hands trembling as he lifted a blackened but intact metal sphere from the debris. After 3 years of desperate searching, the Luftwaffe had finally recovered what German intelligence considered the most valuable piece of American military technology, the Norden Bombsight. The bomber had been shot down during a daylight raid over the naval yards, its crew killed in the crash. But the bombsight, that mysterious device that allowed American bombers to drop their payloads with terrifying accuracy from 25,000 feet, had survived relatively intact. Richter knew that in his hands rested what the Reich hoped would be a game-changing technological breakthrough. "Get this to Rechlin immediately," Richter ordered his assistant, referring to the Luftwaffe's secret testing center. "Highest priority. The Reichsmarshal will want to know about this within hours." What Richter didn't know, what none of the German engineers would understand, until months of frustration later, was that he was holding not a technological prize, but evidence of an unbridgeable gap between American and German industrial capability. The Norden bombsight would become a symbol not of German ingenuity, but of the fundamental differences between the two nations' approaches to warfare, manufacturing, and precision engineering. The obsession with the Norden bombsight had consumed German military intelligence since 1940. Reports from German agents in America before the war had described it in almost mythical terms, a device so precise that bombardiers joked they could drop a bomb into a pickle barrel from 4 miles up. The Americans guarded it fanatically. Bombardiers were sworn to secrecy, trained in isolated facilities, and ordered to destroy the device rather than let it fall into enemy hands. This secrecy only inflamed German curiosity. In a war where strategic bombing was proving decisive, the ability to strike targets with precision could change everything. German bombers, flying with standard mechanical sights, achieved accuracy measured in hundreds of yards. American B-17 seconds, using the Norden, were hitting targets the size of factory buildings from altitudes where anti-aircraft fire was ineffective. General Major Adolf Galland, one of the Luftwaffe's most experienced commanders, had witnessed the difference firsthand. In reports from the Eastern Front and North Africa, German field commanders described American bombing raids that destroyed specific buildings within larger complexes, that severed railway lines at critical junctions, that struck ammunition dumps while leaving surrounding structures intact. "They can see what they're hitting," Galland wrote in a memo to Reichsmarshal Hermann Göring in February 1943. "Our bombers drop their loads in the general vicinity of targets and hope. The Americans select, aim, and strike, with a precision that suggests they possess technology we cannot match with our current methods." Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The race to acquire a Norden bombsight had been ongoing since 1941. German intelligence services had attempted multiple approaches, recruiting American factory workers, bribing Air Corps personnel, even planning commando raids on American bases in England. All had failed. The Americans had implemented security measures that seemed paranoid even by German standards. Each Norden bombsight had a serial number tracked from manufacture to deployment. Bombardiers signed for their devices like bank managers accepting gold reserves. Before every mission, the sight was carried to the aircraft in a locked case. After landing, it was removed immediately and returned to a secure facility. If a bomber was badly damaged and forced to ditch over the ocean or crash land in enemy territory, standing orders required the bombardier to destroy the site with a thermite grenade specifically designed for that purpose. The Germans had recovered dozens of crashed B-17 seconds, but every bombsight had been destroyed, melted into slag, shattered by explosions, or smashed by desperate crew members before capture, until June 27, 1943. The bomber that crashed in Wilhelmshaven had been hit by flak during its bombing run. The explosion had killed the bombardier instantly and started fires throughout the aircraft. The pilot had managed to maintain control long enough to clear the city before the plane came apart in mid-air. The bombardier's compartment, including the Norden sight, had separated from the fuselage and crashed into a muddy field outside the city. The soft earth had cushioned the impact. The bombsight, designed to survive the vibrations and stresses of high-altitude flight, had remained largely intact. When Richter's team excavated it from the wreckage, they found themselves looking at a device that seemed almost alien in its complexity. The Norden Mark XV was a masterpiece of American precision engineering, a gyroscope-stabilized analog computer containing over 2,000 individual parts, weighing 65 pounds, and capable of calculating bomb trajectories while compensating for altitude, airspeed, wind drift, and the Earth's rotation. The device looked like something from a science fiction novel. Two main components dominated the assembly. The stabilizer, which used gyroscopes to maintain a stable platform regardless of the aircraft's movements, and the sight head, which allowed the bombardier to track the target and feed corrections into the computer. Between these components ran a maze of gears, cams, bearings, and mechanical linkages of breathtaking precision. "Photograph everything before we move it," Richter ordered. "Document the position of every component. We may never get another chance like this." The team worked through the night, taking hundreds of photographs from every angle. They sketched diagrams, measured dimensions, and carefully noted how components connected to each other. By dawn, they had created a preliminary technical file that filled 2 briefcases. The bombsight itself was packed in foam rubber, placed in a wooden crate, and loaded onto a truck for the journey to Rechlin. At Rechlin, the Luftwaffe's most experienced engineers gathered to examine the prize. Dr. Hermann Föttinger, who had designed bombsights for the Luftwaffe since 1935, was given the honor of the first detailed examination. He spent 6 hours studying the device with magnifying glasses, micrometers, and calipers, taking measurements and making notes. His preliminary report, submitted that evening to Luftwaffe Command, was both awed and troubled. "This device represents the highest achievement in mechanical analog computing I have ever witnessed," Föttinger wrote. "The precision of its components exceeds anything we currently manufacture. The complexity of its calculating mechanisms is extraordinary. However, I must note with concern that replicating this device will require capabilities that may exceed our current industrial capacity." That last sentence would prove prophetic, though at the time few took it seriously. Germany had excellent engineers, sophisticated factories, and a tradition of precision manufacturing dating back centuries. Surely, German ingenuity could duplicate anything the Americans had built. The reverse engineering project was assigned to a special task force, codenamed Unternehmen Adlerauge, Operation Eagle Eye. Dr. Föttinger was appointed technical director, with a team of 50 engineers, machinists, and technicians drawn from Germany's finest aviation facilities. They were given unlimited access to materials, tools, and support staff. Reichsmarschall Göring himself declared the project a top priority, ranking with the development of jet fighters and rockets. The team began by completely disassembling the Norden Bombsight. Each component was catalogued, measured, sketched, and analyzed. They discovered quickly that the Americans had not designed this device for easy replication. Many components were manufactured to tolerances that pushed the boundaries of what German equipment could measure, let alone reproduce. The gyroscopes, for instance, were marvels of precision engineering. Each rotor was balanced so precisely that it could spin at 10,000 revolutions per minute for hours without deviation. The bearings supporting these rotors were manufactured to tolerances of 1/10,000th of an inch dimensions, so small that German measuring equipment could barely detect the variations. "We can measure these tolerances," reported Hauptmann Werner Schulz, the team's lead machinist, "but I'm not certain we can manufacture to them. These bearings are smoother than anything I've seen in German production. The Americans must have manufacturing processes we're unfamiliar with." The gears presented another challenge. The Norden used dozens of precision gears, some no larger than a fingernail, meshing together in complex trains that performed the sight's calculations. These gears were cut with such precision that their teeth engaged smoothly and quietly, transmitting forces with minimal friction or backlash. German gear-cutting equipment, while sophisticated, could not match this precision. Test gears cut to the Norden specifications showed variations that would cause excessive wear, noise, and eventually failure. The Germans could cut gears precisely enough for aircraft engines and tank transmissions, but the Norden required a level of precision reserved in Germany for laboratory instruments. It's as if they designed this sight to be manufactured on equipment we don't possess, Fürtinger noted in his journal. Every component pushes our manufacturing capabilities to their limits or beyond. It's not that we lack the theoretical knowledge, we understand how each part works. But the practical challenge of making these parts to the required specifications is formidable. The most frustrating aspect was that the Americans seemed to have achieved this precision in mass production. Intelligence reports indicated that Norden had produced thousands of these bomb sites, thousands of devices, each containing components that German engineers could barely manufacture one at a time in laboratory conditions. By August 1943, 2 months into the project, the team had successfully created detailed technical drawings of every component. They understood the theory of operation completely. They could explain how each gear, cam, and linkage contributed to the site's calculating functions. What they couldn't do was build a working copy. The first test components began emerging from German machine shops in September. The results were disappointing. Gyroscope rotors that should have spun smoothly wobbled perceptibly. Things that should have operated silently squealed and generated excessive friction. Gears that should have meshed precisely showed visible gaps and irregular wear patterns. "We're achieving tolerances of 1/1000th of an inch," Schultz reported. "The Americans are working to 10 times that precision. It's not that our machinists lack skill, they're the best in Germany. But our equipment, our measuring instruments, our quality control processes aren't designed for this level of precision." The problem extended beyond manufacturing. The Norden Bombsight used dozens of specialized materials, each chosen for specific properties. The gyroscope rotors were made from a beryllium copper alloy that provided strength without magnetic interference. German metallurgists could identify the alloy's composition but struggled to replicate its exact properties. Small variations in heat treatment or impurity levels affected the rotor's performance significantly. The electrical components presented their own challenges. The Norden used precision potentiometers, rheostats, and switches manufactured to exacting specifications. German electrical components, perfectly adequate for radio equipment and fire control systems, introduced too much resistance variation for the bombsight's sensitive circuits. By October 1943, 4 months into the project, Fürtinger submitted a progress report that was honest to the point of being devastating. "We have successfully reverse-engineered the Norden bombsight's design," he wrote. "We understand its theory of operation completely. However, we have encountered significant obstacles in manufacturing components to the required specifications. Our current industrial capabilities appear insufficient for mass production of this device." The report triggered an immediate response from Luftwaffe Command. How could German engineering, which had produced the world's finest optics, precision instruments, and mechanical devices for decades, be unable to copy an American design? Göring demanded answers. Technical experts were called in to review the project. New resources were allocated. The team was expanded to 75 engineers. The expanded team made little progress. In November, they successfully assembled a prototype using the few components they'd been able to manufacture to acceptable tolerances, supplemented with parts salvaged from the original Norden. The result was a hybrid device that worked barely. Its calculations were accurate enough for testing purposes, but the sight was unreliable, prone to jamming, and required constant adjustment. "It functions," Fürtinger wrote, "but it would be completely unsuitable for combat use. A bombardier would need to recalibrate it before every mission, and even then, its accuracy would be unpredictable. The Americans have built something that works reliably under combat conditions, with vibration, temperature changes, and the stresses of high-altitude flight. Our copy works in a laboratory but would fail in an actual bomber." The fundamental problem was becoming clear. The Norden bombsight wasn't just a clever design, It was a product of an entire industrial ecosystem that Germany lacked. The Americans hadn't just designed a sophisticated device, they'd developed the manufacturing processes, quality control systems, and supply chains necessary to produce it in quantity while maintaining extraordinary precision. In December 1943, a Luftwaffe delegation visited the Zeiss optical works in Jena, hoping that Germany's finest precision manufacturer could solve the production challenges. Zeiss engineers examined the Norden components and delivered a sobering assessment. Yes, they could manufacture many of the parts to the required specifications in their laboratory, by hand, at extraordinary cost in time and resources. But tooling up for mass production would require new equipment, new processes, and years of development work. "What the Americans have achieved," said Dr. Ernst Gundlach, Zeiss's chief engineer, "suggests they've made fundamental advances in precision manufacturing that we weren't aware of. They're not just making these components better than we can, they're making them faster, cheaper, and in larger quantities. This implies manufacturing capabilities that exceed our own by a significant margin." The team at Reich continued working through the winter of 1943–44, but enthusiasm was waning. Each month brought new challenges and few solutions. They discovered that even when they successfully manufactured a component to specifications, it often failed prematurely in testing. The Americans had apparently developed manufacturing processes that not only achieved precision, but also produced components with internal stresses, material properties, and surface finishes that enhanced durability. By January 1944, Fürtinger was facing a personal crisis of confidence. He had spent his career designing bomb sites, had trained at Germany's finest technical universities, had access to Germany's best engineers and machinists, yet he couldn't replicate a device that the Americans were producing by the thousands. His journal entries from this period reveal his growing understanding of what the Norden Bombsight represented. It wasn't just a technical achievement, it was evidence of an industrial philosophy fundamentally different from Germany's. The Americans had invested in manufacturing precision at every level: better machine tools, better measuring instruments, better quality control systems, better worker training. They had built an industrial base capable of producing sophisticated devices not as laboratory curiosities but as routine production items. "We've been competing in the wrong race," Fürtinger wrote in his personal journal. "We focused on designing clever solutions with whatever materials we had available. The Americans focused on building the industrial capacity to manufacture optimal solutions regardless of complexity. They didn't design the Norden to be easy to build, they built the factories capable of producing something extraordinary." February 1944. The Unternehmen Adlerauge team had reached a critical juncture. After 8 months of intensive effort, they possessed not a working copy of the Norden Bombsight, but something perhaps more valuable: a comprehensive understanding of exactly why they were failing. The gap between German and American industrial capability was being measured in micrometers, but its implications were strategic. Fürtinger convened a technical conference at Reich to assess the situation honestly. Present were representatives from Germany's major manufacturing firms: Zeiss, Siemens, Bosch, Krupp, and Daimler-Benz. The Luftwaffe's technical staff attended, along with representatives from the Reich Ministry of Armaments and War Production. What emerged from 3 days of frank discussion was a portrait of American industrial superiority that shocked even experienced engineers. The conference began with a component-by-component analysis of the Norden Bombsight, identifying specific obstacles to German replication. The findings were documented in a report that would remain classified until the 1980 seconds. But its conclusions were unambiguous. American manufacturing had achieved capabilities that Germany could not match, not through any single breakthrough, but through systematic investment in precision at every level of production. The gyroscope assembly illustrated the problem perfectly. The Norden's gyroscopes were the heart of its stabilization system, maintaining a level reference plane regardless of the aircraft's motion. Each gyroscope consisted of a rotor spinning at 10,000 revolutions per minute within a housing, supported by bearings that had to be nearly frictionless. Oberingenieur Rudolf Meyer, from the Zeiss works, presented an analysis that left the room silent. We examined the gyroscope rotor under our finest microscopes, Meyer explained. The surface finish is extraordinary. We measured roughness values of 0.5 micrometers, half a millionth of a meter. Our best production processes achieve 2 to 3 micrometers. This isn't just better, it's a different category of precision. The implications extended beyond the rotor itself. Such smooth surfaces reduced friction dramatically, allowing the gyroscope to spin for hours with minimal power consumption and maximum stability. German gyroscopes, with rougher surfaces, generated more heat, required more power, and lost accuracy faster. But here's what troubles me most, Meyer continued. These aren't hand-polished laboratory specimens. The wear patterns and manufacturing marks indicate these were mass-produced. The Americans have automated processes that achieve surface finishes we can only accomplish by hand, one piece at a time. The bearings supporting the gyroscope presented similar challenges. The Norden used miniature ball bearings, manufactured to incredible precision. Each bearing ball was spherical to within 50-millionths of an inch, a tolerance that German engineers could measure but not reliably achieve in production. Hauptmann Werner Schulz, the team's lead machinist, had spent weeks trying to manufacture equivalent bearings. Our bearing manufacturers are excellent, Schulz reported. They produce bearings for aircraft engines, machine tools, everything we build, but they're working to tolerances of 1/1000th of an inch. The Norden bearings are 10 times more precise. When I showed our samples to engineers at SKF, Germany's premier bearing manufacturer, they said, achieving such precision in mass production would require completely new grinding equipment, new quality control instruments, and new manufacturing processes they'd need years to develop. The gear trains presented another dimension of the problem. The Norden used dozens of precision gears, some cut with teeth so fine they were barely visible to the naked eye. These gears meshed together with almost no backlash, the slight gap between gear teeth that was standard in German precision gears. Dippel. Ing. Franz Weber, from Daimler-Benz's precision department, had attempted to duplicate the gear trains. His report was sobering. We can cut gears to the required specifications, Weber explained, but only on our finest gear-cutting equipment, running at slow speeds. With preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now, back to the story. Frequent tool replacement. The cost in time and resources is prohibitive. A gear we can examine under a microscope and see is perfect, will show deviations under coordinate measuring. The Americans are achieving precision that requires measuring equipment we don't routinely use in production. Weber had made another disturbing discovery. When German manufactured gears were tested under load, they wore rapidly. The American gears, even after hours of operation, showed minimal wear. They're not just more precisely manufactured, Weber reported. The materials themselves are superior. The case hardening, the surface treatment. Something about their manufacturing process produces gears that are both more precise and more durable. This pattern repeated across every major component. The electrical potentiometers used precision-wound wire resistors with resistance values accurate to 1%. German electrical components typically varied by 5% or more. The mechanical linkages used bushings manufactured to tolerances that eliminated play without binding a balance. German machinists achieved through careful hand-fitting, but which the Americans apparently accomplished in routine production. Perhaps most frustrating was the site's optical system. Germany had led the world in optical manufacturing for decades. Zeiss lenses equipped cameras, microscopes, and telescopes worldwide. Yet, the Norden's optics revealed American advances that German engineers found difficult to accept. Dr. Ernst Gundlach from Zeiss presented an analysis of the site's telescope. The glass quality is superb, Gundlach reported. The coatings on the lenses are sophisticated multi-layer anti-reflection coatings that we've only recently begun experimenting with. But what surprises me most is the mechanical mounting. The lenses are positioned and secured with a precision that rivals our finest laboratory instruments. This isn't just good optical design, it's manufacturing excellence. The mounting system used threaded retaining rings cut so precisely that they could position lenses to tolerances of 1/10,000th of an inch. German optical instruments achieved similar precision through painstaking hand adjustment by skilled technicians. The Norden appeared to achieve it through precise manufacturing that eliminated the need for hand fitting. This suggests, Gundlach continued, that the Americans have machine tools capable of cutting threads more precisely than our standard equipment. More than that, they apparently use such precision routinely, not just for special applications. In nearly every area, mechanical precision, surface finishes, material quality, manufacturing tolerances, American production exceeded German capabilities, not dramatically in any single dimension, but consistently across the board. The cumulative effect was a device that Germany couldn't replicate, despite understanding its design completely. General Major Adolf Galland, observing the conference, cut through the technical details to ask the strategic question: why? How did the Americans achieve this industrial superiority? What do they have that we lack? The answer, pieced together from intelligence reports and the team's analysis, revealed fundamental differences in how the two nations approached manufacturing. Investment in machine tools. American industry had spent the 1,930 seconds, even during the Depression, upgrading manufacturing equipment. Companies like Cincinnati Milling Machine, Brown and Sharp, and More Tools had developed machine tools capable of achieving and measuring precision that exceeded anything in standard German production. These weren't laboratory curiosities, they were production equipment installed in factories across America. German industry, restricted by the Versailles Treaty until 1933, and then rapidly rearming, had focused on quantity over ultimate precision. German machine tools were excellent for their intended purposes, producing reliable tanks, aircraft, and artillery in large numbers. But they weren't designed for the level of precision the Norden required. The Americans, reported Dr. Friedrich Müller from the Reich Ministry of Armaments, apparently made a strategic decision to invest in manufacturing precision across their entire industrial base. Not just in a few specialized facilities, but everywhere. They built an ecosystem of precision. Quality control systems. The Norden Bombsight revealed American quality control that exceeded German practice. Each component was apparently inspected during and after manufacture, with rejected parts sent back for rework or scrapping. The Americans had developed statistical quality control methods pioneered by engineers like Walter Schuhart and W. Edwards Deming that identified manufacturing problems before they resulted in defective components. German quality control, while rigorous by European standards, relied more heavily on final inspection than process control. Components were manufactured, then inspected. Americans were inspecting during manufacture, catching deviations before time and materials were wasted on defective parts. Specialization and scale. Intelligence reports suggested that Norden Incorporated, the company manufacturing the bomb sights, had built entire factories dedicated to producing specific components. One facility manufactured nothing but gyroscopes, another produced only the gear trains. This specialization allowed optimization of manufacturing processes for each component type. German production, constrained by Allied bombing and resource shortages, couldn't afford such specialization. Facilities had to be flexible, capable of producing whatever was needed most urgently. This flexibility came at the cost of optimal precision for any specific component. Oberst Hans-Joachim Hermann, from Luftwaffe Technical Intelligence, had compiled reports from German agents still operating in neutral countries. The Americans, Hermann reported, established the Norden factory in a network of suppliers spanning the entire country. Components come from dozens of different manufacturers, all working to the same specifications. This suggests they've standardized precision manufacturing across their entire defense industry. The contrast with German practice was stark. German aircraft manufacturers were largely self-sufficient, producing most components in-house. This vertical integration made them less dependent on outside suppliers, but limited their access to specialized expertise and equipment. Material science. Analysis of the Norden components revealed American advantages in metallurgy that hadn't been apparent until close examination. The beryllium-copper alloy used in gyroscope rotors combined strength, low weight, and non-magnetic properties in a mixture that German metallurgists struggled to duplicate. The aluminum alloys used in structural components showed heat treatments that produced optimal combinations of strength and machinability. "What we're seeing," reported Dr. Klaus Weber from Krupp's metallurgical laboratory, "is evidence that the Americans have made advances in material science that we haven't matched. These aren't exotic materials, they're practical alloys designed for manufacture, but they're optimized in ways that suggest systematic research we haven't conducted." German metallurgy was excellent for its primary applications, armor plate, gun barrels, engine blocks, but precision instruments required different material properties, and here American research had apparently advanced further. The most sobering realization came when the team attempted to cost out manufacturing a German copy of the Norden Bombsight. Even assuming they solved all the technical challenges, the manufacturing cost would be astronomical. Hauptmann Friedrich Schmidt, the team's production engineer, presented estimates that shocked the conference. "If we could manufacture all components to specifications, which we currently cannot, the unit cost would be approximately 45,000 Reichsmarks per bombsight. For comparison, we produce the standard German Lotfe 7 bombsight for 1,200 Reichsmarks. The Americans, intelligence suggested, were producing Norden bombsights for approximately $8,000 each, roughly 20,000 Reichsmarks at exchange rates. They were manufacturing a device of far greater precision for less than half what it would cost Germany to produce. This disparity," Schmidt continued, "reflects the Americans' investment in precision manufacturing infrastructure. They've built factories optimized for precision production. We're trying to achieve precision using equipment designed for different purposes. It's like trying to perform surgery with carpentry tools, theoretically possible, but extremely difficult and expensive." The conference concluded with a series of recommendations that essentially admitted defeat. The team recommended continued analysis of the Norden design to understand American engineering principles, selective adoption of specific innovations that German industry could manufacture, abandonment of any attempt to directly copy the Norden bombsight, development of a simplified German design incorporating lessons learned, long-term investment in precision manufacturing capabilities for post-war. Industry General Major Galland, summarizing the findings for Luftwaffe Command, was blunt. "The Norden bombsight reveals that America possesses industrial capabilities significantly exceeding our own in precision manufacturing. This superiority isn't limited to bombsights, it likely extends to other sophisticated military systems. We cannot match their precision with our current industrial base." The report triggered intense debate within the Luftwaffe. Some officers refused to believe that German engineering could be inferior to American. Others argued that the findings were exaggerated, that the team had simply encountered temporary technical obstacles. But those who understood manufacturing recognized the truth. Germany was fighting an enemy whose industrial sophistication exceeded their own. Reichsmarschall Göring, presented with the findings, was reportedly furious. He had assured Hitler that German technology was superior to American. The Norden analysis suggested otherwise. According to witnesses, Göring initially demanded that the team redouble their efforts, insisting that German ingenuity could overcome any obstacle. Dr. Föttinger, requested to attend a meeting with Göring, apparently stood firm. "Herr Reichsmarschall, we understand the design completely. The obstacles aren't intellectual, they're industrial. We lack the manufacturing infrastructure the Americans have built. No amount of effort will change this fact without years of investment in new equipment and processes." Göring eventually accepted the reality, though he ordered that news of the failure be classified at the highest level. Germany couldn't afford to admit publicly that it had captured an advanced American weapon and failed to copy it. By March 1944, 9 months after recovering the Norden bombsight, the Unternehmen Adlerauge team was reassigned. Some engineers returned to conventional bombsight development, applying lessons learned. Others joined projects deemed more critical to Germany's deteriorating military situation. The Norden bombsight itself remained at Reich, a monument to the limits of German industrial capability. Dr. Foetinger submitted a final report that would remain classified for decades. Its conclusion was prophetic. The Norden bombsight demonstrates that America has achieved a level of precision manufacturing that we cannot currently match. This suggests they possess similar advantages across other military technologies. Unless Germany can close this manufacturing gap, we will face increasing technological disadvantage as the war continues. The team had achieved their goal. They understood the Norden bombsight completely, but understanding and replicating were different challenges. They had discovered that American industrial might wasn't just about size or resources. It was about systematic investment in precision at every level of manufacturing, about building an industrial base capable of producing sophisticated devices as routine production items rather than laboratory curiosities. The Norden bombsight had revealed a truth that many German engineers found difficult to accept. In the realm of precision manufacturing, America had pulled ahead, and in modern warfare, where victory often depended on which side could produce more sophisticated weapons more quickly, this advantage could prove decisive. April 1944. As the Unternehmen Adlerauge team dispersed, and their findings circulated through carefully restricted channels, a few perceptive German analysts began to understand the broader implications of their failure. The inability to copy the Norden bombsight wasn't an isolated technical setback. It was a symptom of deeper structural disadvantages in Germany's industrial competition with America. Oberst Hans-Joachim Hermann, Chief of Luftwaffe Technical Intelligence, compiled a classified assessment that drew connections between the Norden failure and other disturbing intelligence about American weapons development. His report, dated the 15th of April 1944, opened with a stark warning. The Norden bombsight should be understood not as an exceptional achievement, but as representative of American industrial capabilities. We must assume that similar precision manufacturing advantages extend across their entire weapons production. Hermann's analysis proved prescient. As German intelligence gathered more information about American weapons systems throughout 1944, a pattern emerged that validated the lessons of the Norden bombsight project. The proximity fuse represented another example of American manufacturing sophistication that Germany could not match. These miniature radar systems, small enough to fit inside an artillery shell, detonated explosives at the optimal distance from their target. Each fuse contained a vacuum tube radio transmitter and receiver, a power supply, and processing circuits, all built to withstand the 20,000 G acceleration of being fired from a cannon. When German forces recovered unexploded American artillery shells in Italy in early 1944, technical analysis revealed devices of stunning sophistication. The proximity fuses used miniature vacuum tubes manufactured with precision that German electronics firms deemed impossible for mass production. The tubes had to survive extraordinary mechanical stresses, while maintaining electrical characteristics within tight tolerances. Wilhelm Meyer, from the Reich Research Council, examined captured proximity fuses and reported findings that echoed the Norden bombsight analysis. The Americans have manufactured over 1 million of these devices, Meyer wrote. Each one contains components we couldn't produce in quantity in laboratory conditions, yet they're manufacturing them by the thousands daily. This suggests manufacturing capabilities that exceed our own by a substantial margin. The pattern continued with radar systems. American shipboard and airborne radar was proving consistently superior to German equivalents. When a captured B-17 yielded its radar bombing system in early 1944, German engineers discovered precision manufacturing throughout. The radar's magnetron tube operated at frequencies that required tolerances German manufacturers struggled to achieve. The waveguides were machined to smoothness that matched the Norden bombsight's components, The antenna positioning systems used bearings and gears of familiar precision. Generalleutnant Wolfgang Martini, head of the Luftwaffe Signals Service, drew uncomfortable conclusions. In a May 1944 report, American radar components consistently show manufacturing precision exceeding our standards. This isn't random, it reflects systematic capability. We should assume that any American system requiring precision manufacturing will demonstrate similar advantages. The strategic implications extended beyond individual weapons systems. If America possessed across-the-board advantages in precision manufacturing, they could produce not just more weapons, but more sophisticated weapons. In a technological arms race, Germany was competing with one arm tied behind its back. The Norden Bombsight failure highlighted another critical difference: America's approach to military technology development. The Germans had traditionally focused on developing clever solutions with available resources. American development philosophy appeared different: design optimal solutions, then build the manufacturing capacity to produce them. This philosophical difference manifested in aircraft design. German fighters like the Bf-109 and Fw-190 were masterpieces of engineering sophisticated aircraft designed to be manufactured with available materials and processes. They used simple landing gear, minimal electrical systems, and components that German industry could produce in quantity. American fighters like the P-51 Mustang represented a different philosophy. The Mustang featured a laminar flow wing that required precise manufacturing to achieve its aerodynamic advantages. It used a liquid-cooled engine that demanded precision manufacturing of pumps, radiators, and coolant systems. The cockpit contained sophisticated instruments and electrical systems built to higher standards than German equivalents. When Luftwaffe pilots captured or examined American aircraft, they frequently commented on the quality of construction. Parts fit precisely without hand-fitting. Electrical systems were reliable and well-engineered. Manufacturing quality exceeded German standards even for mass-produced aircraft. Oberst Hermann's April 1944 report included testimony from test pilots who had flown captured American aircraft. "The Americans don't build cheap aircraft quickly," reported Major Heinz Baer, a decorated ace who had test-flown a captured P-51. "They build expensive aircraft quickly. Every system shows quality construction. This suggests they can afford to manufacture to higher standards while still producing in large quantities." This observation cut to the heart of Germany's industrial dilemma. Germany was manufacturing weapons designed for rapid, economical production, yet still couldn't match American output. America was manufacturing weapons designed to higher standards and still producing more. The mathematics were devastating. Intelligence estimates suggested America was producing 96,000 aircraft annually by mid-1944, more than Germany's total production for the entire war. These weren't simple aircraft, they were sophisticated bombers, fighters, and transport planes incorporating advanced systems. Each B-17 bomber contained over 400,000 parts. Each P-51 fighter featured sophisticated systems that would have been limited to prototype aircraft in Germany. America was somehow achieving both quantity and quality, mass production and precision manufacturing. For German planners trying to understand how the war had turned so decisively against them, the Norden Bombsight provided uncomfortable answers. By summer 1944, the strategic situation made the Norden Bombsight's lessons tragically relevant. American bombers using these sophisticated sights were systematically destroying Germany's industrial capacity. They were hitting synthetic fuel plants with precision that shut down production for weeks. They were striking ball-bearing factories, disrupting manufacturing across multiple industries. They were demolishing marshalling yards, severing transportation networks. The irony wasn't lost on German observers. America's superior precision manufacturing had produced bomb sights that enabled precise destruction of Germany's less sophisticated manufacturing base. The industrial advantage revealed by the Norden analysis was being used to widen that advantage further. Dr. Fottinger, now working on defensive systems at Reich, wrote in his journal in June 1944, We spent months trying to understand how the Americans achieved such precision manufacturing. Now we watch daily as that. Precision is used to destroy what manufacturing capacity we retain. The Norden Bombsight wasn't just a weapon, it was evidence of industrial superiority we couldn't match. Some German engineers who had worked on the Norden project began applying its lessons to improvised solutions. If Germany couldn't match American precision, perhaps they could develop weapons that didn't require it. This thinking contributed to development of weapons like the Fritz X guided bomb and the V1 flying bomb systems that used simpler guidance methods but could still strike strategic targets. But these adaptations couldn't close the fundamental gap. Germany was innovating to work around limitations while America was investing to eliminate them. The trajectory was unsustainable. By late 1944, the manufacturing advantages revealed by the Norden analysis were manifesting across all military technology. American trucks were more reliable than German equivalents. American radios featured better frequency, stability, and signal quality. American field artillery used fire control systems of greater sophistication. In every category requiring precision manufacturing, American equipment demonstrated advantages. The impact on military effectiveness was cumulative. More reliable equipment meant fewer breakdowns, less maintenance, higher operational readiness. Better radios meant clearer communications and better coordination. More precise bomb sights meant fewer bombing missions needed to destroy targets. Superior manufacturing quality was translating into combat advantage across the board. General Oberst Alfred Jodl, Chief of Operations for the Wehrmacht, received briefings on American industrial capabilities in August 1944. According to witnesses, Jodl's response captured the despair spreading through German leadership. "We are fighting 1945's war with 1940's manufacturing capability against an enemy using 1950's industrial technology. The gap is not closable with our current resources." Norden Bombsight project had become a classified case study in Germany's industrial limitations, circulated among technical officers as a cautionary tale. Its lessons informed realistic assessments of what German industry could and couldn't achieve. Engineers learned to design weapons suited to German manufacturing capabilities rather than pursuing optimal solutions that industry couldn't produce. This defensive adaptation came too late. By autumn 1944, Allied armies were pressing into Germany from east and west. Strategic bombing had crippled industrial production. Resource shortages limited manufacturing regardless of capability. The industrial competition that the Norden bombsight had illuminated was effectively over. Dr. Fürtinger spent the final months of the war at Rechlin, watching as Allied bombing reduced Germany's remaining industrial capacity to rubble. In February 1945, he made his final journal entry about the Norden bombsight. "We recovered it 20 months ago, believing it would provide advantages we desperately needed. Instead, it revealed disadvantages we couldn't overcome. Perhaps that was its true value, forcing us to see reality clearly, even if too late to matter." When American forces captured Rechlin in April 1945, they found the Norden bombsight still there, carefully preserved in its laboratory case. Nearby were thousands of pages of German analysis, technical drawings, and test reports documenting the failed replication attempt. American intelligence officers were astounded by the thoroughness of the German work and by their inability to translate understanding into production. Major Robert Patterson, an ordnance officer with the advancing American forces, examined the German documentation and wrote in his report, "The Germans understood the Norden bombsight as well as we do. Their technical analysis is impeccable, but they couldn't manufacture it." This failure tells us more about relative industrial capabilities than any amount of production statistics. Post-war interrogation of German engineers who had worked on the project provided additional insights. Many expressed frustration that their work had been wasted, but also grudging admiration for American industrial achievement. Dr. Fürtinger, interviewed by American Technical Intelligence in June 1945, was remarkably candid. "You must understand that German engineers are trained to be resourceful, to accomplish much with limited means. This served us well in many applications. But the Norden bombsight required something different: unlimited precision, perfect materials, optimal manufacturing processes. You had built an industrial system capable of producing such devices routinely. We had not. That difference, more than any tactical or strategic factor, determined the war's outcome. The Norden bombsight failure resonated beyond immediate military implications. As Germany faced reconstruction after the war, some engineers argued that rebuilding should prioritize the kind of precision manufacturing infrastructure that America had developed. The bombsight became a symbol of what modern industry required, not just skilled workers and good designs, but systematic investment in manufacturing capability at every level. West Germany's post-war economic miracle would eventually incorporate these lessons. German industry rebuilt with an emphasis on precision manufacturing, quality control, and systematic process improvement. Companies like Bosch, Siemens, and Zeiss emerged from the war determined to match and exceed American manufacturing standards. The humiliation of being unable to copy the Norden bombsight motivated a generation of German engineers to ensure such limitations wouldn't recur. By the 1960 seconds, West German manufacturing had achieved parity with American precision in many areas. The nation's reputation for engineering excellence and quality manufacturing became proverbial. Analysts studying this recovery often pointed to wartime experiences, particularly projects like Unternehmen Adlerauge, as catalysts for post-war improvements. Dr. Hermann Fottinger, who survived the war and became a professor of mechanical engineering at Technical University Munich, lectured frequently on the Norden bombsight episode. His talks, drawing on his wartime journals, emphasized that the failure had been instructive. We learned that manufacturing capability is as important as design brilliance, that systematic investment in precision infrastructure matters more than individual ingenuity, that quality cannot be improvised, only developed through patient improvement of processes, equipment, and standards. The Norden bombsight itself became something of a legend in engineering education. Its extreme precision and sophisticated design made it a teaching example of what was possible when manufacturing excellence met engineering ambition. But the German failure to copy it provided equally valuable lessons about industrial capability, systematic development, and the limits of reverse engineering. For historians studying the Allied victory in World War II, the Norden bombsight episode offers insights beyond traditional military analysis. Yes, the Allies had numerical superiority, better strategy, and greater resources, but they also had systematic advantages in manufacturing sophistication that compounded their other benefits. Germany's 18-month failure to copy the Norden bombsight revealed industrial limitations that affected everything from radar to aircraft engines to fire control systems. These limitations weren't absolute. German engineering produced remarkable weapons throughout the war, but they were consistent enough to create cumulative disadvantage in the technological competition that modern warfare had become. The bombsight's lesson was ultimately strategic. In industrial warfare, manufacturing capability matters as much as military capability. Design brilliance without production capacity means little. Understanding enemy technology without the means to replicate it offers limited advantage. Victory flows to the side that can not only invent but also produce sophisticated weapons in quantity. The Norden bombsight, that precision instrument recovered from a crashed bomber in June 1943, had revealed truths that many German leaders found difficult to accept. America wasn't just bigger or richer, it was more industrially sophisticated. The United States had built a manufacturing infrastructure capable of producing precision devices as routine products, not laboratory curiosities. Germany had challenged this industrial colossus with courage, ingenuity, and tactical brilliance. But courage cannot overcome ball bearings manufactured to insufficient precision. Ingenuity cannot compensate for grinding equipment that cannot achieve required tolerances. Tactical brilliance matters little when the enemy's bombsights can destroy your factories from altitudes where your fighters cannot reach. The German engineers, who spent 18 months trying to copy the Norden bombsight, learned these lessons intimately. They returned to conventional bombsight development with new appreciation for the relationship between design, ambition, and manufacturing capability. They became more realistic about what German industry could produce, more humble about German technological advantages, more aware of American industrial strengths. For the broader course of the war, their failure mattered less than what it revealed. Germany was fighting an enemy whose industrial sophistication exceeded its own in critical areas. This advantage compounded over time, allowing America to field increasingly sophisticated weapons, while Germany struggled to maintain production of existing designs. The Norden Bombsight, that device of 2,000 precisely manufactured parts, had proven to be more than a weapons system. It was a message, written in gears and gyroscopes and precision optics, about the nature of modern industrial power. Germany had received that message, understood it completely, and discovered too late that understanding couldn't overcome the manufacturing gap. In the end, 18 months of German engineering effort had produced not a working copy of the Norden Bombsight, but a sobering realization. They were competing against an industrial system that had evolved beyond their own. The device that had fallen from the sky over Wilhelmshaven had delivered an education far more valuable and far more devastating than any bombing raid. The lesson remained relevant long after the war ended. In industrial competition, systematic investment in manufacturing capability matters more than individual brilliance. America had built that capability patiently over decades. Germany had discovered its absence in 18 months of frustrated effort. The difference had helped decide a world war,